Hello and welcome to our final video on our topic on functions and graphs. Today we've got a slightly longer video as we're going to be looking at a very important part to our topic on functions and graph, and questions to do with this topic will come up in almost any exam or past paper that you see, and this is on graph transformations. So I'm going to start off this video by explaining to you what a graph transformation is. Now, throughout the topic on functions and graphs, we have talked about functions, for example, g of x, and we have talked about what the graph of particular functions might look like. So when we sketch a function, we call it the graph of the function, and for this graph here on the left, we would call this a cubic function, and on this one on the right we would call it a sine wave, which we also called a trigonometric function. So we've got a cubic function here and a trigonometric function. Now in today's video we're going to be talking about transformations of these two graphs, in particular a cubic graph, which as we can see might look something like this. This is just a little example, but when we talk about graph transformations, we are simply talking about things you can do to this function g of x, so adding things, subtracting things, multiplying things to this, to make this graph look slightly different, to transform this graph. And at higher, we will be talking about three different types of transformations, the first of which is called a translation. Now, to define what we mean by a translation, we will say that a translation moves every point on a graph a fixed distance in the same direction. We'll also say this does not change the shape of the graph. And that final sentence is very important. So what we're saying here is that a translation will simply move every point along the graph a particular number of distance, a particular distance. Every point will move the same distance in the same direction. And we say that this does not change the shape of the graph, so it will always look the same. So the first type of translation we're going to talk about is a translation parallel to the y-axis. So we'll say translation parallel to the y-axis, because there's going to be two different types of translations, one which is parallel to the y-axis, and as you can guess, a translation which is parallel to the x-axis. Now let's say we have a function, we'll call it f of x. If I was to take this function f of x and add a value on the end, let's say f of x plus a, where a is some number, the value a will shift the graph either up or down. But in which case will it do this? Well, if a is positive, the graph will simply be moved up. So if a is positive, we'll say it like that, a positive, it will shift the graph up. So we can see here our original cubic graph, as you can see, has the points 1, 1, 0, PQ, and 3, 0. We can see here they've all been shifted up by a value of 1. So in this case, our function is now g of x plus 1. A is positive, so every coordinate, every point on this graph will be shifted up 1. Now if it's being shifted up 1, every y value will now be y plus 1. So instead of minus 1, 0, we've got minus 1, 1. Instead of PQ, we now have PQ plus 1. And instead of 3, 0, we now have 3, 1. And we can't work out any of these other points, so we'll just connect them just like our graph looked like. So we can see here the shape of the graph has not changed, but every coordinate has been moved a fixed distance. In this case, it's 1 up because A is positive. In this case here, we have our sine graph again, and we're doing sine x plus 1. So A is positive, and as we can see, the graph has just been shifted up in the y-axis by 1 for every single point. Now, what if A is a negative number? So instead, let's say our g of x now becomes gx minus 2. Well, if A is going to be negative, as you can see, the graph goes down in the y-axis by whatever the distance, well, the distance is going to be whatever this A value is. So as you can see, everything here has been shifted down by minus 2. So our point minus 1, 0 is now minus 1, minus 2. Our point PQ is now PQ minus 1. And our point 3, 0 is now 3 minus 2. And we can see the same sort of thing has happened here with sine x. It's now sine x minus 1. So everything has been shifted down in the y-axis by minus 1. So this is a translation parallel to the y-axis. So now we're going to look at a translation parallel to the x-axis. Now, because it's a translation, again, there's going to be another shifting involved here with every single point. So in this case, if we have a function f of x, if this time the value a, whether it's positive or negative, if it's within inside the brackets, so f of x plus a instead of f of x plus a, this time it will translate the graph parallel to the x-axis. And a nice way of remembering this is it's inside the bracket, so it's being added on to x. So it must be parallel to the x-axis. Whereas if it was outside of the brackets, it's not next to x, so it's not got anything to do with the x-axis. That's my way of remembering it anyways. So in this case, let's take a look where a is positive. So if we have a being positive, in this case, well, it simply shifts the graph left. So you might think it would shift it right, but it simply shifts the graph parallel to the x-axis. So every x coordinate will be changing by the value a. So in this case, if our function g of x is now g of x plus 1, every point will be shifted in the x-axis left by 1, or whatever a is. So it's a bit confusing for this one, but if it's positive, just think of it as it gets closer to 0. So as you can see, the point minus 1, 0 is now minus 2, 0. PQ, which is the general point, we say is now P minus 1, or P minus whatever A is, Q. And the point 3, 0 is now 2, 0. And we can see here with sine x plus 90, so because it's inside the brackets, the period is going to be shifted, as we can see that it is going to be shifted along the x-axis by 90 degrees to the left. So it previously starts at 0, now starts at minus 90 degrees. And as you can imagine, when a is negative, it's simply just going to be the other way around. It's going to go away from the, it's simply just going to go away from the x-axis by whatever the value of a is. So in this case, our a is minus 2, because instead of g of x, we've got g of x minus 2. So it's negative. So every x coordinate is going to change by 2 to the right. So this point here, which was minus 1, 0, is now 1, 0. This point here, which was PQ, again, this is the general point. We can see here the x coordinate is simply increasing by 2 because it's moving away, and Q just stays the same. And then if we take a look at this sine graph, we can see again that this time it's been shifted to the right by 90. So it starts at 90 degrees, and you can see generally what's happening here. So these are translations, which is the first type of a graph transformation. So the next type of graph transformations we're going to be taking a look at are reflections. So a reflection, again, we'll start off with a bit of a general definition. We'll just simply say that a reflection, as you can imagine, what a reflection does, it simply flips the graph. Now, depending on where we're flipping it, it basically flips the graph about one of the axes. So we'll look at both cases like we did with translations right now. So it's important that when reflecting, we know that it flips about one of the axes, and it's important that we apply this transformation before any translation. So again, here we've drawn in our two generic graphs. We've got a cubic graph, and we have the sine wave again. The first reflection we're going to look like, similarly to translations, there's two. The first one we're going to look at is a reflection in the x-axis. So in this case, if we have a function, let's say f of x, a reflection will always have something to do with multiplying by -1 or multiplying by a negative. So a reflection in the x-axis will take our function f of x and simply stick a minus in front of it. So minus f of x. Now in this case, when we have a negative in front of our f of x, it simply reflects the graph of f of x in the x-axis. So it flips it about the x-axis. So if we take a look at our graph of g of x up here, we can see it looks something like this. If we are flipping it about the x-axis, every point will move to the other side of the x-axis by the same amount of distance it is from the x-axis. So as you can see, this point here, -1, 0 is going to stay where it is, but everything above this is simply going to flip to be down. And as you can see, this point here, PQ, is going to become P minus Q. You can see the x coordinate again staying the same, but the y coordinate will be changed with a negative in front of it. And this point here, again, 3, 0 will just stay 3, 0. So one thing we notice with this is that every y coordinate is just being multiplied by -1. So we can see it's being flipped about the x-axis. And the same works with our sine. If we've got minus sine x instead of just sine x this time, we can see it's simply going to get flipped upside down. So every y coordinate is becoming minus y now. And again, we also have another type of reflection, and this is a reflection this time in the y-axis, which is again quite similar to the x-axis, except this time our negative is going to be within inside the bracket. So instead of minus f of x, we're doing f of minus x. Now this time our way of remembering it from a translation about the fact that because it's next to the x, it's to do with the x. This time it's not, because it's a reflection and it's next to the x. There is a way that we do like to remember it though by doing this. Well, if we take a look at what a reflection in the y-axis looks like, we can simply see that this is just doing the -1 thing times by the x coordinate. So as we can see our point PQ, if we times the x coordinate by -1, as it looks like this is doing, we can see that this is reflecting it about the y-axis, and our x coordinate, which was P, is now minus P. And we can see every other coordinate here is simply becoming minus whatever its x is, y. So it flips about the y-axis. And we can see the same here is happening with sine x. So we can see sine of minus x, again, is just simply changing the x coordinate to be minus x. So the last type of transformation, graph transformation we're going to be looking at higher is scaling. And this is to do with scale factors. So we're going to start off again by defining what we mean by scaling. We say a scaling stretches, and it's important we use the word stretches instead of shifts or flips. So if you remember, a shift is a translation, a flip is a reflection, a scaling stretches or compresses. We'll look at both cases. So it stretches or compresses the graph along one of the axes. And again, we'll look at two cases. We'll look at scaling a graph vertically, and we'll look at scaling a graph horizontally. So scaling can be one of the more confusing ones, and I'll go over in as best detail as I can how we can scale a graph, starting with scaling vertically. So again, I'm going to start with our two initial graphs here. We've got a cubic graph and we've got our sine graph. If we have a function, for example, f of x again, we've looked at adding a number to it, so f of x plus a. We've looked at multiplying it by -1, so minus f of x. The last thing we're going to look at is if we multiply f of x by a value, say k. So let's say k times f of x. In this case, because we are multiplying by a value k, we say that this will simply stretch or compress the graph. And we're going to look at the two cases. The first case for when k is greater than 1, and the second case for when k is between the values 1 and 0. And the reason we're looking at it between 1 and 0 is because if it's less than 0, it becomes negative. And as we remember, if it's negative, well, that will also do a bit, it will also do a bit of reflecting. So here I have put in our two instances. As we can see, the y-coordinate of each point on the graph is going to be multiplied by the value of k. However, the roots are going to be unaffected. So if we look at the examples here for values of positive k, so if k is a value that, well, obviously it's going to be positive for both cases, but for the case where k is positive and greater than 1, we can see that this here has simply taken our graph here and multiplied everything by 2, because we're doing y equals 2 times g of x. So in this case, it's simply going to stretch the y-coordinate by 2. So every y-coordinate is going to become 2y. So as we can see, the graph is being stretched. So I will also just write here that this stretches the graph. And this is very important that we say stretches. So as we can see here, PQ is now P2Q because the value of K is 2. If it were y equals 3gx, this would be P3q. So everything's being multiplied by 3. And as you can see, it does look very similar, but it's just being stretched. So this point will be higher up, but the graph will overall keep its general sort of shape, but it will look slightly different. And here we have y equals 2 sine x. In this case, it's going to stretch the graph, so its y value now becomes 2y. So instead of this point here being 91, it's going to be 92. The roots will stay the same, so it will be 0 at 0 and 180, as we can see. However, it's just being stretched by a value of k. Now, if k is between 0 and 1, so not equal to 1, but if it's not equal to 0 as well, if it's between these two, for example, a half, we say that it compresses. So again here, I don't really have space at the end, but I'll just write compresses. So in this case, it's going to compress the graph, which is just the opposite of stretches. And because it's multiplying it by a fraction, as you would expect, it will shrink the graph. So the value PQ now becomes P whatever K is Q. So in our case, it's a half. So it's going to be P a half Q. So we can see our graph getting skinnier, it's being compressed. And in this example here, it's a half sine x, and it's looking like this pretty skinny graph now of y equals a half sine x, where every y value is simply now a half of what it was before. So we're going to do the exact same thing here, except we're going to be looking at scaling horizontally this time. And as you can imagine, this time, instead of the k being outside the bracket, the k is going to be within inside the bracket. So if we take a function f of x, and let's say we multiply x by a value k, so f kx, this time this is going to scale the graph of f of x in the horizontal direction. And we can remember this by the value is next to x, so it's going to shift our x coordinate, or not shift, it's going to stretch or compress our x coordinate. And we can take a look at this, and we'll also see how the y-axis intercept will stay the same. So we'll first look at the scenario where k is greater than 1. When k is greater than 1, we can see our x coordinate is simply being compressed by whatever the value of k is. And this is within according to the x-axis. So as we can see here, because our graph was previously g of x, we can see here, if we multiply it by g, let's say 2x, this time the graph is being compressed. So as we can see, the value pq is now a half pq. This is because we're dividing it by 2. So every point will be divided by 2. And as you can see, a similar thing is going on here with the sine graph. Every x coordinate is being divided by 2. And in the second scenario, where k is between 1 and 0, let's say it like that, this time it's going to stretch the graph. So every point will become 2 times whatever it is. So as we can see here, we have the function of g of x, but this time we're doing g of a half x. Now, although it's a bit trippy because this time it's a fraction and it's between 0 and 1, this time it actually is going to stretch it as it becomes 2pq instead of pq in this case. And as we can see here, a similar thing is going on with the sine wave. So those are all our kinds of graph transformations. I am going to go over a few examples as it can be quite confusing. We've learned quite a lot in today's video. But before I get into them, I'm going to quickly talk about the order that we do transformations in, as we might get some multiple transformations in the same question. So the order that we do this in is that we make sure we begin by doing the reflection first. So if there's a reflection involved, so if we have a negative involved in our, if we're given a function f of x and we're asked to sketch, let's say negative 2 f of x, we need to make sure we always do a reflection first. And once we've done this, we can then do any translations or scaling as such. So we'll go into a few examples that might have multiple of these involved, or some that might just have one involved, and we'll show you how we can sketch graph transformations. So in this example here, we are told that the graph of y equals some function f of x is shown below. And we can see the graph here, and we instantly notice that f of x is some sort of cubic function. So if you remember what the translations, the scaling, or the reflections of a cubic function look like, that'll be very handy for this. And we are asked to sketch the graph of y equals. Now we can see we've got two transformations involved here. We've got a reflection because we've got minus in front of our f of x. And this time we've also got a translation because we've got minus 2. So we've got some sort of value a at the end, which is going to be minus 2. So as we said, we need to begin by doing a reflection, and then we need to do our translation. And let's see what they're going to look like. Well, first we have our negative is going to be outside the f of x. So if you remember, when it's outside, what we do is we are simply reflecting it about the x-axis because it's not next to the x, so we're doing it about the x-axis, just to remind us. And we've also got the negative value a, so we know that we're going to shift it to the right. Oh, it's outside of the bracket, sorry. So it's going to be shifted down. That's my bad. So it's going to be shifted down the y-axis. So this is just to help me memorize this. So let's go into what this is going to look like. Well, firstly, the best thing to do is just take the points that you do know and say what they're going to be on our graph now. So we have the point 0, 0. We know that it's going to be reflected, which won't change it, but we know it's going to be translated down the y-axis by a value of whatever a is, which is 2. So this point, instead of 0, 0, is going to be 0 minus 2. So all we're simply going to do, put a little marker here, say that it's going to be minus 2, because that's going to be one of our points, so the y-axis intercept. The next point we have is 10 divided by 3, 4. Now, because we are reflecting it about the x-axis, we know the y-coordinate is going to change, and we're simply just going to stick a negative in front of it. So we're going to have 10, 3, comma, minus 4, but we are also doing a translation. So the y-coordinate is also going to go down by 2. So instead of 10 minus 4, 10 over 3 minus 4, it's going to be 10 over 3 minus 6. So let's pop that in somewhere about, doesn't have to be exact, but we'll go about here. And we'll just label it 10 over 3 minus 6. And our final coordinate is 5, 0, which is going to be very similar to what we did here. The 5 is going to stay the same. The 0 is going to become, well, technically negative 0. And then we're simply going to take 2 off. So it's going to become 5 minus 2. So we'll pop that about here, actually. So we'll put 5 minus 2. And all that's left to do is join up the dots. So we know it's going to look something like this. Now this could end up being very bad here, but as long as we keep the overall shape of the graph, we know it's going to go down from here because we reflected it. So it's actually going to go a bit more steep than that, but that should be the general idea of what the graph will look like. So this is going to be our last example, and we are asked to sketch the graph of y equals 5 cos 2x. Now, this time we're looking at a trigonometric function instead of sine though, however, it's going to be cos. And if we remember our cos graph, this is just very rough. Looks something like this. It starts up at 1, it goes down before coming back up, and we'll just let us know that this is going to be 1, this is going to be minus 1, and it's also important that we know that this continues on, and this is just one period of cos. So we mark that by doing dotted lines, so we know that it just continues on from there, and we know that the period is 360. It's important we know this because it looks like we're doing some sort of scaling involved. And as we remember, we need to start with any reflections. Luckily for us, we don't have any reflections because we've not got a negative. However, we do have some 5 cos 2x. So we've got a 5 on the outside. Now, what did we do when we had a 5 on the outside of our function? Well, we simply said that all this is going to do is stretch the graph by whatever the value of k is. So we're going to start with having a scaling. Actually, looks like we've got two different kinds of scaling involved. We've got a scaling with the vertical and a scaling with the horizontal. So this could get a bit confusing, but we'll try and explain it as best as we can. So we've got scaling horizontally first. And what did we say? Well, we just stretch the graph by multiplying every y coordinate by whatever k is. So it used to start at 1, it's now going to start at 5, which whatever our k value is. So instead of 0, 1, it's going to be 0, 5. So it's going to look pretty similar anyway. Again, we know that the point down here it's going to get to is going to be -5. However, we have a second scaling. We have a scaling vertically. And this is because our 2x here, or 2 times x, is within inside the bracket. So when we scale horizontally, we are simply, in this case, our k is greater than 1. And if you remember, when it's greater than 1, it actually compresses the graph a little bit, corresponding to the x-axis. So in this case, instead of our period finishing at 360, it's going to finish at 180. And this is because our previous value of, let's say, 0.90 is now going to be 0.5 because it's 2. So it's going to be 0.45, which is going to be somewhere here. So we know it's going to cross the x-axis here. And then halfway between at 90, it's actually going to be down at -5. So we'll mark that in. So it's going to go up through here, cross at about 45, come down at 90 at -5, before coming back up about here, and then it will get back up to -5 at 180. So if we draw that in, see if we can do it, it's going to look something like this. It's going to get to a minimum at -5, come back up. I completely missed that point, but we'll just make it bigger and then get back up to the top there like that. And we'll just do a dotted line to say that that is the end of that period. And that is what our cos graph will look like in this case. Of course, it will continue on from there and do the same, and so on and so forth. So we can see in this case, we've done 2 different kinds of scaling. So it's important to get your head around these. Just do lots of examples and you'll hopefully pick up on the ways of remembering if you're scaling a particular axis or translating across parallel to a particular axis, or if you're doing some sort of reflection across an axis.